Hey everyone. So, what do we have today? Well, we'll be discussing about some smart contracts and some attack vectors which are very less known and are not so famous in this world. So, we'll have a look onto that. So, brief introduction. My name is Tejas Rastogi. You can just call me Tej because my name is pretty hard to pronounce. And what I do, I'm a security auditor and researcher at Consensus Diligence, and the creator, founder of these things. ReserSec is a security community, CipherShots is a CTF platform, and Unchained is again a security conference for blockchain and all the cryptography stuff. And this is my Twitter. Like, if you want to connect with me, I'm here. Awesome. Cool. So this is the agenda. We have a lot of attack vectors, and we have to cover these many in this talk. So we'll be quick, but I'll make sure to give you a demo for these, or at least show you how they work and look like. All right. Okay, first one, call data. So what is actually the call data? Like, if you take it in simpler terms, like people who are hearing this word for the first time, like if you want to interact with a smart contract, you want to create a transaction, you want to initiate or execute a transaction, you need some data, right? So these data can be sent through message call. So simply any input data in a message call is a call data. Like if you are interacting with a smart contract, or one smart contract is interacting with another smart contract, it needs some data, right, for the call. So that is what the call data is. So below you can see a function. So it's func, and it's taking two parameters, A and B, and what it does simply just adds two parameters and gives you the result. So below is what the call data looks like. So the white part, the 4 bytes, is the function signature, which is made up of the hash, the Kachak hash of the data types of the parameters, and the first 4 bytes of the resulting hash is what the function signature is. And after that is the ABI encoded parameters. So if you have a data type which is less than 32 bytes, it will be encoded into the 32 bytes. So here you can see A is 02 at the very this part. So this is the first parameter, this is the second parameter, these are ABI encoded into 32 bytes. Alright, and this is the function signature. Alright, so this is a demonstration of how ABI encoding looks like. Good, great. So moving on to the first vector, which is the dirty higher order bits. So let's say we have a function called func, which is taking a uint8. So basically what we need, a 1 byte parameter, right? uint8, just need 1 byte. So here you can see I have passed like 23, which is 17 in hex, and these are ABI encoded. And you can see the call data. The green is the function signature, and then there's a parameter. Great. So you must be wondering, like, it's just uint8. So what the compiler needs and wants is just 1 byte, right? So typically it should look like the first one, this one. This is like what compiler wants. But what if we pass some extra bits to it, this call data, right? So it is still 17 in hex, right? Because it's a uint8 parameter. So this is actually not needed, right? So technically the compiler should avoid or ignore this data type, this value, this FF, and just consider or concern about this 17 at the last. But it doesn't actually work like that. Alright, so this is the screenshot for the compiler. Let's take where it actually works. So in compiler versions 0.8 and ahead, you can see that how the values are being processed. Firstly, it is taking our call data, which we have passed, the FF and the 17 one, right? Now is doing a logical AND with the FF, right? That's what we want. That's what the compiler wants, just one byte, right? Which is technically right. And after that, this is done. This is just to extract the last value, the last byte. And after that, after extracting the value, it's actually verifying whether the extracted value is actually equal to the call data we have passed, right? So we have passed FF00017, and 17 was the value we want, or the compiler wanted. So firstly, it extracted the value, and after that, it again did a EQ operation to verify or validate whether the extracted value is actually what we wanted, right? But it doesn't actually work like that in compiler versions behind or previous to 0.8. What actually happens, it just extracts the value and doesn't validate it, right? So what's the attack vector? Imagine you have some assembly code, and what you're trying to do, you're trying to validate or trying to process some raw call data. So right now, here you can see, I'm trying to store the call data like Y4, because the first 4 bytes are the function signature, right? So we are taking the parameter, the first parameter, and storing it into the slot or in the storage. Simple as that. But it is assembly, right? It is assembly. We don't have the solidity housekeeping opcodes going on. So we are just processing the raw bytecode or the raw opcodes, right? So what it will do, it will just capture all the call data, all the parameters, like this whole value, instead of just concerned about this last byte because we are passing a uint 8, right? It will take the whole value and store in the slot, right? So imagine you are storing some prices and all, and you're just passing 1 byte value, and the attacker knows this thing and goes ahead and stores or gives you a random call data with 30 higher order bits, or like adding some extra bits. So what you have, instead of having a 256, like in the range of 0 to 255 value of price, it can manipulate any value, or it can give you any price, what he wants, what she wants, right? So this is one thing with the call data. The second thing is malleability, right? So we always want to work with the assembly or write optimized code. So let's understand this thing with the help of example, right? So we have a function pawn, which is just taking a base32 value, and it's just making sure here that it is not a null value. It should contain something, and it should be a valid one, just a random logic. Here, what we are trying to do, we are hashing the data. Message.data is the call data. We are hashing the value to just make sure that it should not be allowed again. It should be allowed only once, right? Here you can see if I pass in the same message.data again, it will just check whether we have that value in the mapping or not. If we already have it, it will just fail and my transaction will fail, correct? But what if I add some data? I append some data to the call data, all right? So here we have the logical data which the function wants, which is the correct one. And what we are trying to do, we are trying to make a hash or unique value from this call data, right? So firstly, let's say you have given this call data, right? And you are done. Now, according to the check, you are not allowed to pass the same call data again, right? You're not allowed to pass the same token value again, the base32 value, correct? So this is fine, but again, we have given the same token. We have given the same base32 value, right? So it will go here, everything will work. This will work because we have given the right token, correct? But what we are hashing the whole call data. This one. So this is my function signature. This is the base32 token, which is same for all the calls. And this is the appended bit that we have passed. And now both the hashes are different. So we have technically bypassed these checks, right? And made our token verified again, correct? So these are some of the attacks you can do for the call data. And how we can protect it? Just don't use it. Just don't use assembly, right? Or if you are using it, just make sure what are the disadvantages of these raw processing and involve some checks to avoid these things. Pretty straightforward, and there is a CDF challenge that I've created. If you want, you can go ahead and solve it, try to solve it. So, okay, moving ahead. Now, the second one is gas griefing. So what is actually gas? Well, in simpler terms, just like your car runs on fuel, transaction also runs on fuel, right? So for the transaction, the fuel is a unit gas. So like why we need gas? Well, every transaction needs some instruction set to be processed, some opcodes to run on the EVM. And for that, you need to send some value, to let them execute the transaction, correct? This is cut out from the yellow paper if you want to read it, but just avoid it, right? Next thing you want to know is EIP 150. What EIP 150 says that all the subcall or the subcall context can only consume this much amount of gas. Like, what is the subcontext? Subcontext is basically like a smart contract making a external call or making a subcall to another smart contract. Like for example, here you can see contract A is making a low level call to contract B, and this is a subcall. So it says, EIP 150 says that the subcalls can only consume this much amount of number, which is approx 63 by 64 of the gas of the parent remaining. For instance, let's say there was around 500 gas here, then there will be 63 of 64th of the gas will be sent to the subcall, right? Simple as that. Now let's talk about the gas griefing. Now we know that in order to make our transaction, to execute our transaction, we need some gas, right? But what if we can control our transaction, like how these are executed? Like what if we partially execute a transaction, right? So this is a cool thing. So for instance, you know that a subcall needs a 63 of 64 gas of the parent. But what if we calculate it and give it our accordingly value that this should work, the above operations work, but this subcall is not getting enough gas to execute entirely. So what will happen? This will silently fail and the rest of the operation will work. So your top level transaction is still working, but your subcall is failing, right? So now imagine you are interacting with a function that is giving you some shares and taking some tokens out of you, right? Just a trade, like you're giving 500 tokens and getting 500 shares. But the above operations are giving you some shares, but the important call, which is to take tokens from you, is failing. So you're basically getting some shares for free into a protocol, right? And that's what it is all about, right? So here you can see, this is a subcall and going to the contract B, and contract B is doing some operations, but we have calculated the exact value such that this internal transaction of this subcall is failing and the top level call will work, right? So this is one attack vector related to the gas, and this is not so popular, and oftentimes we overlook these things while doing code reviews, audit, or even development. Cool. And this is not enough. Now we have a CDF challenge as well, called as Maya. And if you want to try, you can go ahead and try to solve it. Cool. Now a second variant of gas griefing. Let's do some denial of service. Cool. So now we have seen that we can partially execute a transaction, right? What if we deliberately exhaust all the gas and it will all happen on the caller side, right? So we are not the one who are facing these gas issues. This will be on the caller side. So let's see that. So a possible scenario can be a subcaller hook, right, to an address. Let's say a transaction is giving a subcall to a attacker control address or your address. And what you're trying to do, you are just exhausting all the gas that have been supplied to you, right? So you're deliberately making the transaction fail, right? Where it can be used, for instance, there can be a scenario where this call is very important to be executed in order to process the rest of the instruction. Like, have you ever played some CDF challenges like King of the Hill, right? Yes. So in King of the Hill, what happens is if a new user wants to be the new king, what the function will do, it will send the ether of the last king to the last king, so such that it can make you the new king. So for it to execute entirely, it is very important to send the last king its contribution. But let's imagine the last king is an attacker and doesn't want to be dethroned, right? So what it can do, it can just simply make this transaction exhaust entirely, and if the transaction is not executing, it's not being dethroned. It's the forever king. Cool. So how we can do that? With the help of return data copy. So this is an opcode, and this is being used for the subcalls, right? So here you can see that, like just we discussed, a low-level subcall, right? And it actually returns a success value, whether the call succeeded or not, and the return data. But the problem is, whether you want it or not, this return data copy will always be there in the instruction set, right? So whether you want the return data or not, it will still be copied, right? So what we can do, let's pick up the same example, right? So this is a function X, and we are doing a subcall or a low-level call to contract B. And what contract B is trying to do is just randomly copying a very large chunk of memory, right? We don't have any goal. We just want the gas to be exhausted, right? So what will happen? You must be wondering, right, that, okay, that it will only get 63 of 64 of gas, right? And let's say it is consuming all the gas, but still we have 1/64 of the gas remaining to complete the entire transaction, right? But it doesn't work like that. This copying of memory actually happens in the top level transaction and not with the 63 of 64 gas that you got, right? So right now what we are trying to do is randomly copying like what we have or what we can do with the gas supply to just make the function fail. That's what we want, and that's what the attackers want, right? So that's how we can make a denial of service scenario with the gas grieving, right? Moving on, again a CDF, if you want to try, there is one. Cool. Moving ahead. All right. Now this one is cool, and this is all about uncached values. So let's imagine you have a function, right, which is giving you two different values for the same transaction, for the same call. Let's say you call the function X, it is returning 5, and the next time it is returning 10 in the same transaction, right? Now you must be saying, okay, yeah, that's pretty easy. I'll just have a state counter, right? Like I will just check whether my function has been called previously or not. If yes, I will just update the value, right? I will just return 10. Simple as that. For the first time, I will return 5. For the second time, I will return 10. But what if we have a view function? We cannot update the state, right? So now that's interesting, right? So what we can do, we can still do some magic, right? How? With the gas left. So gas left is a special opcode, not so special, but yeah, special opcode, which actually returns the left, like the remaining gas right now, whenever you call it. So let's see this function, right? So I've just created a random example. There might be some other scenarios in the real life world, but let's take this one. So there is minimum price 500. We just want to make sure that the oracle I'm trying to call is not giving me some bad values. So oracle is an external actor. I'm calling the oracle to fetch some price and making sure it should be greater than the minimum price, right? So I believe it will work, right? Because I'm making sure I'm not getting a value less than 500, right? It will always be greater than 500, right? Simple as that. But here and here, what you're gonna get a different value both the time in the same transaction, and we have not updated the state. How? Let's see that. So for the first time, oracle.price gonna fetch the price function, And what it's gonna do, it's gonna check that what is the gas left right now. If it's less than this value, I'll return 0, else 500. So for the first time, obviously there will be enough gas for this function call. So what it's gonna return, it's gonna return 500 to just validate the conditional check, right? So here, what it's gonna return 500, and what we have done, we have validated this conditional check that this is fine. The price that I've returned is correct and perfect. You should go ahead with it. The next time you're calling the same function, right? We are still in the same transaction. We have not updated the state, right? But again, if you call it, as there are already some opcodes that have already executed, now the gas remaining is less than 11,800. Now, what will happen? It will actually return you 0 instead of 500, right? So what you have right now, the current price is 0, even we have not updated the state. In the same transaction, what we have done, we have bypassed the conditional check, and we have given the victim a wrong value or a 0 price, and we can do whatever we want. And how we can prevent this thing? Well, we are not caching these values. Just make sure if you're calling a view function from now onwards, just make sure you're caching the value and using the cached value again instead of calling that function twice, right? So this is a new vector recently discovered, and people should take care of it. Cool. All right, the next one is metamorphic contracts. So what are metamorphic contracts? All right, so you must have worked or at least heard about upgradable contracts, right? So what are upgradable contracts? Simple as that. Like, okay, let's talk about the fundamental of blockchain, right? You know that the deployed code, the deployed contract is immutable, right? Right. It cannot be modified, cannot be changed, correct? Right. What is the upgradable contract? It's basically two different contracts, one for the state and one for the logic. So proxy contains the state, implementation contains the logic. So whenever you make a call, the proxy contract makes a delegate call to the implementation, and it executes the logic and updates the state in the proxy contract, right? Simple as that. But what if we don't want this scenario, right? Because we know, right, there are two different contracts, and if the implementation is upgraded, I will be able to know the address, right? The new updated address, right? What if we want the same contract to be modified altogether? We want to ruin the fundamentals of blockchain? Yes, kind of, we are doing that. But how we are doing that? With the help of self-destruct. So what's the purpose of self-destruct is to destroy the code deployed on address and redeploy a new contract, right? So that's what we are trying to do. Cool. So for this, it's better to show you from implementation. So if you head over to this link I've added in my slide from Ethereum blockchain developer, you will find an implementation doing the same thing. All right. So what we are trying to do, first we took the bytecode of the contract that you want to deploy first, right? Then this is the metamorphic contract or code that we'll be deploying very soon. Cool. And firstly, what we are trying to do here is we are pre-calculating the address of the metamorphic contract. How we can do that? With the help of create2. So create2 is an opcode which lets you to calculate the address on which the contract will be deployed pre-handed, right? So that's what we are trying. Why we are doing that, we'll get to know soon. So here, a little bit of assembly. What we are trying to do is just deploying our implementation contract or the contract we want to be modified, correct? So let's say the contract we want to modify is contract A. So here we have just deployed that contract A and stored that value, stored that address into the implementation of mapping, correct? Here, what we are trying to do, we are creating, now we are deploying the metamorphic code. What was the metamorphic code? Simply this one. Now, what this is trying to do, we'll look into that as well. Cool. So let's now look into that. So what it's trying to do, if you can see it, if I can zoom it a bit, I'll just quickly run down what these opcodes are doing. here. Cool. So we are making some stack here. Push 1, tip 2, PC, push. So these are all the parameters for the static call. So first what we are trying to do is store a value. Let me show you. Let me first run these. Cool. So what we have done, we have stored this value, this 4 bytes value, into the memory location 0. And what this is basically the function signature of this function get implementation. So we have stored it, and now the remaining opcodes are trying to make a static call, and these are the parameters of the static call. So basically we are calling this function to give me the address of the contract A that we want to be modified, correct? And cool, we'll make a static call. After that, ext code size. Now it will check what is the size of that address stored at the contract, and then simply copy ext code copy. Simply copy the size, or simply copy the code that is deployed on that address. Right. So overall, let me give you a plain process that is happening. Is simply this one. First we deploy the factory, right? We have calculated the bytecode of the Metamorphic contract, and then deploy the implementation code which we want to modify, or the contract A, or the attacker's code, we can say. Save that into a mapping, because we have just seen that the opcodes are trying to fetch the function which will give it the address stored into the mapping, right? Deploy the contract of Metamorphic bytecode. Cool. That is done. Now that we have just seen what's happening with the bytecode, and now we want to modify. Now we want to upgrade the contract on the same address itself, right? So what we can do, we will self-destruct, we'll destroy our first address, or the first contract A, or attacker's code, and we'll deploy a different one, a modified version of the same contract on the same address. And now what will happen? Now you know the process, right? Now what's the attack impact of this? Let's say you have a contract, right, which a protocol is referring to let's again consider an Oracle, right? Now Oracle, or let's say a math library, right? Or a math library which is referring to your contract, right, to give you A plus B, right? What you have done, you have just modified the logic to now give A plus 2B, right? So how it can impact? Well, for non-technical people, they will never be able to know, because the address is same. We have not shifted to another address. We are still on the same address. The same address is now having a different logic from the previous one. And this is what metamorphism is all about, to give you some different logic on the same address, right? Cool. Now, till yet, what we were talking about were some Web3 attack vector itself. But Web3 all alone is kind of boring. We want some cool stuff as well, right? Let's mix Web3 with Web2 as well. So our old very favorite attack vectors like accesses, all the other code injections, right? Let's do that as well, right? Because Web3 is not all about smart contracts. It's about the front end as well, right? Because protocols, you must have seen and interacted with their project sites, right? Fetching values from their smart contracts, all that stuff. Cool. So what if we are allowed to store any value in the storage, and that's being fetched on the front end and without any sanitization, right? Let's say a contract is storing usernames, right? Let's say my name, Tejas, right? But how it's being processed on the front end? Simply inner HTML, right? The front end or the front page is rendering the storage from the smart contract. So what I can do, I can actually put a script into the storage, and that will be rendered onto the front page. What I can do some HTML injection, I can do accesses and all the stuff, And that's the cool thing, right? We are mixing Web3 and Web2 together, right? And that's not it. We can do SQL injections as well, right? That's a cool idea. And okay, that's another example. That's a practical one, right? You must have visited OpenSea before for the NFTs, right? So then you must be knowing about token URIs, ERC-721, 1155. Have you heard about it? Or maybe work with it, right? A simple token is standard, NFT token is standard. And how OpenSea, so every NFT has a token URI, and what token URI does is simply like it contains some characteristics of your NFT, right? Like what's the trade, like if it's Dogecoin, like how famous is Doge, right? How's the fur, all the stuff, is it expensive or not? So like the basic stuff, right? And how it processes that, it fetches the data from the token URI and renders the page or makes the page out of it, right? Now imagine the token URI or the values that are being fetched are not sanitized, and now you're allowed to store any script, right? Or any HTML code. So imagine here at the properties, instead of giving it a name, you are giving it an HTML page. And how you can, what you can do with it, you can create a login page here to fish some value or do some fishing here, right? So you're just saying, hey, I've created a NFT page for you. Just go ahead and log into it. Give me your password and you will get your NFT, right? Basically, it doesn't work like that, but you're getting your victim's password, correct? So this is a practical example. OpenSea doesn't work like that, so don't try on that. But yeah, there will be many more platforms, and there are platforms which do that. And the worst part is, what if it is executing the script? Instead of rendering, what if there is a JavaScript exec function executing whatever is there in the token URI, right? So what we can do, probably RCEs and pop some shells, right? So that will be a cool thing. So from the Web3 storage, from just a smart contract, we are now able to create an RCE as well in the Web2 world, right? Beauty of both the worlds, correct? Cool. Now we are on our last topic. I wanted to add more patterns, but the time was less. Cool. So there are some bad patterns as well. And let's see one, static call and stale memory. So what is a static call? Static call is just the same low-level call or the message call, but you're not allowed to modify the state. Right? If you're attempting to modify a state, if you're attempting to update a state, it is not allowed. It will revert, right? But what if it still creates a problem? Great. So let's see an example. All right. So here you can see a function which is making a static call to a target address, and for the understanding, I have stored some value in the memory location 0, and here I'm just checking whether what was the value at that location prior to making the static call and after making the static call. And this is just the success value, whether the low level call succeeded or not, correct? And what we are trying to call is a random function which is returning some value, let's say 5,000. Now this is the outcome of these values. If the call succeeded and everything was working fine, no attacker involved, correct? So what was the value? First, I stored a value like FFFF at this location 0, and after the call, what I'm trying to do here is the return data of this call I'm trying to store at the same memory location, which is memory location 0. So technically, what it should do, it should override my previous value, right? So, which is what's happening here. Earlier I had FFFF, and for the call, because it succeeded, now it had this value, right? It's successfully overwritten that, and the status was 1. 1 means succeeded, correct? Everything is working fine, technically correct. What if we do a revert? So it's the same thing happening here, but instead of like relying on this success of this call, what I'm trying to do, I'm just randomly reverting my function. Let's say you're trying to call my function, I'm just reverting it. I don't care what you're trying to call, I just want to revert. I don't have any goal. Yeah, simple as that. So what it will do, you can see the success was 0, means the call failed, and obviously it will not overwrite my value, the previous value. The value before and after the call will be the same, which is FFFF, right? Now imagine you are just randomly relying on this call and you think, okay, it will always work and I will always be having some value at the memory location 0, some new values, right? The value we want, right? Let's pick up the same example of price, Oracle manipulation, Oracle price. I'm calling an Oracle and I want some price at this memory location, right? And you know that the Oracle will at least give me some value in some range because I trust my Oracle, correct? But randomly someday the Oracle got upgraded and now it's just reverting that function which you're trying to call. Now, instead of giving you a price, it is giving you nothing, right? Now what you're gonna do, you're gonna move ahead with the value you had previously at that memory location. Let's say you already had some memory, let's say some value like this FFFF, right? So your rest of the instruction, your rest of the opcodes, your rest of the logic will now work on this old value. Now this is your price, right? So this is again a bad pattern, and you should always check that if your call is failing, you should not move ahead with the functional logic, right? You should stop right there or revert or bubble the reverting message, right? So with that, I end my talk, and it's time to Q&A. I hope you like it. Right.
Any questions? Everyone's baffled. Okay, then thank you.
All good. Thank you.